Hello dear students, welcome you all. In this lecture, I am going to discuss about the success and failure of liquid drop model, right? So, in the previous lectures, I have discussed in details about the liquid drop model and semi-empirical mass formula. Right? These are the, two things that are linked with each other. Liquid drop model is based on semi-empirical mass formula, and we have seen that what are the outcomes of semi-empirical mass formula. If I'm writing this semi-empirical mass formula here, then it is MAZ, mass of a nucleus that has atomic number Z and mass number A, that is Z time mass of proton plus A minus Z mass of neutron minus B upon C square, or B can write V, volume energy into A, right, minus A surface energy A power 2 by 3 minus Z into Z minus 1 power 1 by A power 1 by 3 into A Coulomb energy, right, minus A symmetry energy into A minus 2Z whole term square divided by A, then plus minus delta comma 0, right. So this was the semi-empirical mass formula that I have derived in the previous lectures. Then we have discussed the condition for mass or atomic number of the most stable isobar. Then we have discussed about the equation of mass parabolas for isobaric nuclei. We have seen right, what is the condition for radioactivity, that is the emission of alpha particle and beta particles, right, which nuclei are prone to this beta decay and alpha decay, right. So all these things has been discussed based upon the semi-empirical mass formula. So now I'm going to summarize the success and failures of these two things, that is liquid drop model and semi-empirical mass formula. So if I come to the first success, then we know very well that this model was and this semi-empirical mass formula was capable of explaining the mass and binding energy of several nuclei, right. You can see we have this formula. Now this formula can be used to calculate the binding energy and mass of a nucleus, right. So when we calculated the mass of different nuclei and binding energy, then it was found that it was correct for several nuclei. I mean, we can say that for most of the time it was correct. So we can say that this formula is quite helpful in explaining the mass and binding energy of several nuclei. As I told you that based upon semi-empirical mass formula, right, by making the use of this formula, I can find out the mass or atomic number of the most stable isobar. I have explained it in earlier lecture that how we can develop a equation that can be used for calculating the atomic number of the most stable isobar for the given number of isobars for a given mass number, right. Now by using the equation of mass parabolas for isobaric nuclei, right, equation of mass parabolas for isobaric nuclei, right, I can make a prediction about the emission of alpha and beta particles from a nucleus. I mean, by making the use of the relation of equation of mass parabola, we can tell that which type of nuclei will be prone to alpha decay and beta decay. In beta decay, we can even predict that which nucleus will undergo beta positive decay and beta negative decay. So all these things can be explained correctly with the help of semi-empirical mass formula or liquid drop model, right. The most important success of this liquid drop model and semi-empirical mass formula was nuclear fission. The nuclear fission, we know very well, it is the process in which a heavy nucleus, right, when it is attacked by a projectile, that is a slow moving neutron, right, this is heavy nucleus, then it split into two lighter nuclei, right. This is nuclear fission. If we understand it in this way, and I'm drawing a rough picture of it, right. When we target a heavy nucleus with a slow moving neutron, then that neutron enter inside the nucleus and it set up oscillations inside the nucleus, right. It is going to deform the shape of the atomic nucleus, right. Instead of spherical, its shape becomes ellipsoidal, and if the oscillations are very high and the energy supplied by the neutron is very high, in that case, I mean, earlier nucleus was of this shape, but when the neutron enter in it, the shape becomes like this, right. Here these are the oscillations. Now its shape get distorted, so now it is trying to regain its shape, but we know that energy has been supplied by the neutron. So the neutron, when it has entered inside the nucleus, it will try to break up this heavy nucleus into two sub nuclei, this one and this one. So this is the way this semi-empirical mass formula and liquid drop model explain the nuclear fission. With the help of this formula, we are capable of explaining which type of nuclei will be prone or easy for undergoing nuclear fission, right. So all these things have been explained correctly, and as I told you that the most important thing in all these successes is the explanation of nuclear fission. So these are the successes. Now I am coming to the failure, right. So if I talk about the failures, then the one and important failure of this model is that it does not explain why the nuclei that has either number of proton, number of neutron, or both equal to 2, 8, 20, 28, 50, 82 or 126. If any nuclei have either Z or N or both equal to any of these number, then those nuclei have extra stability, means they are extremely stable as compared to the nuclei in their neighborhood. So liquid drop model or semi-empirical mass formula is totally silent about it. It is not able to explain why this feature is happening in certain nuclei, and we call these nuclei as magic nuclei and these numbers as magic numbers. So we can say that this liquid drop model is not able to explain magic numbers correctly. The second failure is when we measure the magnetic moments of different nuclei, we make a calculation of magnetic moment for the different nuclei, but this model, liquid drop model and semi-empirical mass formula, both of these are silent about the existence of magnetic dipole moment by the different nuclei, right. So magnetic, we can say that magnetic dipole moment or magnetic moments are not explained, right. The third failure is spin. We have came to know that the all nuclei that exist in nature, they do possess some type of spin, quantum spin, that we call nuclear spin, but this liquid drop model is totally silent about the spin. It is not able to explain the spin of the different nuclei, right. So these are the major failures, right, which lead to the foundation of the subsequent nuclear models, right. One more failure that I want to tell you is that it is unable to tell that why certain nuclei exist in the excited states. Right? It also unable to explain that why nuclei exist in excited states. So these are some important, although there were many failures, but these are some important failures which should be addressed, right? If we want to get a suitable model or exact model of the atomic nucleus, then that model should be answer these 4 questions at least correctly, right? So it laid down the foundation of further models which further explain all these things, right? But although this model has these failures, it is sufficient to explain these different properties of the atomic nucleus, and we know very well that this is the first model that has made an attempt to explain nuclear structure, nuclear properties, right? One more failure that came in my mind is the parity, right? Parity of the different nuclei is also not explained, right, by the liquid drop model, because parity is also an important feature of any nucleus, any quantum particle, quantum entity, quantum thing, right? So parity is also not explained. So these are some success and failures of liquid drop model. Although, as I told you, that this model is first model and quite successful, but still it has lot of drawbacks. So it was modified later on with new models that we will study in the coming lectures, right? So thank you very much.